For the second example in Splines, we'll be using the same data set except finding the power generated at 24 miles per hour using a quadratic spline. So the same data set still exists up top on our page here, except now we'll be using functions of the form fi of x equals a of I x squared plus b I x plus c of I. So each one of these quadratic equations has 3 coefficients to determine, whereas the linear set obviously only had 2, and the inclusion of the x squared term allows us to incorporate some curvature into the joining of points in the system. So there are 5 different data points, 1, 2, 3, 4, 5, each one of those making an xy pair. So we are going to have 4 gaps to fill with equations. So that's 4 equations with 3 coefficients each. That means we're looking at, 12 coefficients. Okay, that's not so bad. Out of this bank of 12 coefficients that we need to figure out, there's some overlap between equations, but we have 8 equations based on boundary conditions. We have 3 equations based on the interior derivatives, so 8 and 3 makes 11, leaving us 1 shy of the number we need. We need either 12 equations, 12 unknowns, or figure out a way to get rid of 1 unknown and go to 11 equations, 11 unknowns. So if you remember from the description of walking through the textbook, the way that quadratic equations are handled, quadratic spline fits are handled, is that they assume that either the first or the last second derivative is blanked out, is 0. So you'll see in this example that they actually choose to blank out the first term, which makes things a little bit more straightforward. So let's go straight to how they apply the first condition of point continuity to this equation form given the data set above. So for I equals 1, so dealing with the first gap, 4 gaps, 4 different i's. So for gap 1, the equation definition would be a1 x1 squared plus b1 x1 plus c1 equals y1. Now we just said this is the first gap where they assume the second derivative is 0. So if we were to take the derivative of this function, it would be 2a1x plus b1. That's not b of I, that's b of 1. And if you take, that's the first derivative, second derivative would be 2a1. If we're everything else is gone. If we set that equal to 0, it's 0. That means nothing more than a1 equals 0 if the curvature of this first element is going to be nothing. So this term is actually gone for that first equation. It's just nuked because a1 for all cases is going to be 0 whenever the curvature of the first gap equation is nothing. So that is the setup, except that there's another pair. The x1, y1 term is the leftmost point, right? That's the left point. We're studying the gap that exists between these first 2 pairs. That's what this equation is going to bridge. So we need to actually also use the same coefficients, x2 plus c1 equals y2. So same coefficients, b1, c1, but the point of reference, x2 and y2, is different now. Those are the points on either side of this gap that the equation must hold true. So in this circumstance, you have 2 unknowns, 2 equations. You could actually directly solve right now for b1 and c1. You can figure out what you're looking for. But we need to move on to I equals 2. So you can start recognizing this pattern and system of determining what the coefficients would be. So for I equals 2, you write out the initial equation again, except now you have coefficients a2. The left-hand side will be based on x2 squared plus b2 x2 plus c2 equals y2. So notice this is based on x2 and y2, the second point. The coefficients stay the same for the right-hand side of this, and that'll be x3, not cubed, x3 squared. I always do that. Plus b2 x3 plus c2 equals y3. So again, we're basing the governing equations off of the x and y pairs that dictate the functional values of the left and right-hand side of that gap, namely The first equation is based on x2, y2. The second equation is based on x3, y3. All right. So that same system carries forward for x equals 1 through x equals 4. The only one that is unique is this first element, and that's to reduce the number of unknowns in our system by 1 so that our 11 equations can adequately solve it. The only equation shift that happens is whenever you start handling derivative continuity across gaps. So if you look all the way back at the first derivatives of the polynomials from adjacent intervals, they have to be equal. So the first equation of merit here for, we'll call this derivative continuity. The equation 1 derivative being equal to equation 2 at the right-hand side would be 2a1 x2 plus b1 equals 2a2 x2 plus b2. That's the derivative of the first equation at the right-hand side, set equal to the derivative of the second gap equation at the left-hand side, both of which plugging in values x2 because that's where the intercept happens, right? That the point x2 is shared between the right-hand side of the first gap equation and the left-hand side of the second gap equation. So this, after some manipulation, arrives at the form b1 minus 2 times 22 a2 minus b2 equals 0. This is a form that would be very easy to plug in to an eventual matrix solution. And if you consider it, we have 1, 2, 3, 4 total gap equations. So there will be 3 connections between those gap equations that will have curvature continuity. So we have a total of 8 point equations. We've covered 4 of those 8 here. I equals 3 and 4 are very similar, just repetition of this I equal 2 stage. And then you have 3 gap equations following the form that we just outlined down here, leading us to a large matrix that I am not going to bother putting in my surface. I'll quickly switch over to the document camera to show you what this solution matrix is going to entail. So that looks fun. This ends up being, I believe, 11 by 11. So let's see here. That's 5, 10, 11. There we go. So notice everything that has to do with a point continuous has a non-zero solution rate. It doesn't have to, but that's just a nice way to look to differentiate. Once you get to curvature continuity, the derivative continuity, those are the last 3 equations in coefficient form here, coefficient linear form. All those have right-hand sides equal to 0. So that is what you get out of the system. This is not a matrix you'd ever want to solve by hand, so you pick your favorite flavor matrix solution method and go to town with it. Here in the example, they used left division, looks like, to divide the matrix A by the solution vector B. You can either invert and multiply, you can use Gauss-Jordan, whatever process you'd like to go through to find the answer until you come all the way down to find the vector of answer coefficients, C. Now keep in mind, that's just part of them. They continue on. There are a lot of different unknowns necessary to define a spline that complex. And then you must split them apart into several different equations. So there are the coefficients listed with all the appropriate names. And then they must be split apart into the different regions of pertinence to us is really only the region containing 24 miles per hour because that's where we wanted to interpolate between. So the solution is pieced together the polynomial for that region from the listed coefficients. You plug in a value of 24 and out comes the solution of 525 watts of output given that splined finish. So really the key to all of this is just setting up the equations properly, following the form for cubic splines given, this is a quadratic spline, and that form is given on page 227, equation 671. It's fairly basic. You're just plugging in all the defined points at the left and right hand side to form the large matrix of point continuous and curvature continuous conditions that have to be followed in all of your coefficients to work out.